Hello dear students. Today we are going to see very important theorem, that is master theorem. This is one of the methodology to solve the recurrence equation. There are mainly three main techniques that are used to solve recurrence equation. First is substitution method, the second one is recurrence tree method, and the third method is master theorem. So today I am going to give you more detail of master theorem. Master theorem is very popular method for solving the recurrence equations. If your recurrence equation is of the form T of n, it is equal to at n divided by b plus theta n raised to k log raised to pn, and if these conditions are satisfied, then we can apply the master theorem. What I mean by these conditions are: a value should be greater than or equal to 1, the value of b should be greater than 1, and value of k should be greater than or equal to 0, and this p should be a real number. If your equation is of the form T of n at n by b plus f of n, then we can apply this master theorem. Now let us try to understand all these terms. What I mean by this n, what this n indicates. So n is the size of the input, while a is the number of subproblems in which you have divided your problem, and n divided by b indicates the size of each subproblems. And we usually know whenever we are having any problem, we are always subdividing our problem into various subproblems, right? And to solve such equation, such recurrence equation, master theorem is being applied. Now this function f of n, now when we divide our whole problem into various sub problems, right, we require to divide the problem, and at the end, once the solution is found, we require to merge the solution, right? So whatever the cost is related to these two operations, for this dividing and for merging, that cost is known as f of n, and it is represented in this function T of n. It is equal to at n by b plus f of n. Let us take one example related to this, and before that, let us try to understand how actually the master theorem works. What are the various cases when you apply the master theorem? So as I discussed earlier, if your equation is of the form T of n, it is equal to at n divided by b plus theta n raised to k log raised to pn, value of a is greater than or equal to 1, value of b is greater than 1, k is greater than or equal to 0, and p is a real number, then what you have to do, you have to find out two things: a, and you have to find out the value of b raised to k. You have to compare both these values. Now there are three possibilities: either the value of a will be greater than b raised to k, or it will be equal, or the value of a will be less than b raised to k. And based on whichever condition is applied, we have to choose the respective case, and based on and after that we also have to check the value of this p, and based on that we are going to decide the time complexity, right? So all these cases will become clear when we go through one example. So let us take one example related to it. Let us say we are given the master theorem that we have to apply for this particular recurrence equation. T of n, it is equal to 3t n divided by 2 plus n square. Now as we know, the general equation for master theorem to be applied is T of n, it is equal to ATn divided by b plus theta n raised to k log raised to Pn. Now if we compare these two equations, this is my first equation, again I am highlighting the same equation, and this equation, if you compare them, here you see T of n is there, T of n is there, here ATn divided by b is there, and here 3t n divided by 2. So here if we compare properly, the value of a will be equal to 3 and the value of b we are getting 2. Theta n raised to k. Now theta is a tight bound, right? And for that, if we are having value here n square, now if we compare with n raised to k, the value of k we are going to get is 2. It's very easy, right? Now here in this equation there is no any other term other than n square, right? But still we are left with here this term, that is log raised to p n. So if we put value of p equal to 0, it will give us log raised to 0 n, and that is 1, right? Then and only then we can say these two equations looks identical, right? So we have considered all these values, that the value of a is equal to 3, value of b it is equal to 2, value of k it is equal to 2, and value of p it is equal to 0. Then what is the next step? We have to find out the value of a, that is a equal to 3, and value of b raised to k. B value of b we know, that is 2, right? So 2 raised to 2, as the value of k it is equal to 2, so that gives us 4. Now if we compare value of a and b raised to k, so a is less than b raised to k, right? And as we know, as per the master theorem, right, the case 3 will be applied. Let me show you that particular thing. That particular thing we have already discussed. Here you see the value of a is less than b raised to k. Let me highlight it for you people. Here the value of a is less than b raised to k. So we can apply the case 3, and here you observe the value of p is less than 0, or it may be p greater than or equal to 0. So the example that we are seeing right now, the value of p is equal to 0. So this time complexity we have to write down. So T of n it is equal to theta n raised to k log raised to p and n. Now what is the next step? We have to put all those values, right? So let us put those values. So T of n it is equal to theta n raised to k log raised to p n. That will gives us T of n it is equal to theta, and the value of k is 2. The value of k is here, you see here it is 2, right? And the value of p is 0, so that is log raised to 0 n, right? And that will give us this log raised to 0, log raised to 0, and that is 1, right? So T of n that we are going to get is theta of n square. Let us take one more example. Now here you see in this case you are given recurrence equation T of n it is equal to 2t n divided by 2 plus n log n. Now if you compare it with the generalized equation T of n it is equal to at n divided by b theta n raised to k log raised to p n. We get the value of a equal to 2, value of b it is equal to 2, value of k it is equal to 1, and value of p it is equal to 1. Again, what is the next step? As we all know, we have to find out the value of a, and we also have to find out the value of b raised to k. Here in this case the value of a is 2 and the b value is 2 and k value is 1. That gives us b raised to k it is equal to 2 raised to 1 and it is equal to 2. So clearly we can see here, if the value of a is also 2 and the value of b raised to k is also 2, so the case 2 will be applied, where a is equal to b raised to k, right? So now we follow case 2, and we also know the value of p is equal to 1. So respective case will be applied, that you can go through those equation, master theorem cases equations, right? So T of n it is equal to theta n raised to log a base b log raised to p plus 1 n. Now if we apply or put all these values, the value of b it is equal to 2, value of a it is equal to 2, and the value of p is equal to 1. We get here theta n raised to log 2 base 2. Here you see log 2 base 2 is nothing but only 1, that value is 1, and log raised to 1 plus 1 n, that gives us square n. So hence we get the time complexity T of n, it is equal to theta n log square n, right? So whenever this kind of recurrence equations are given to you, and if you find that master theorem can be applied, and if that particular example is asked for only by applying master theorem you have to solve, so you have to just apply master theorem only. Then in that case you can't apply any other method like recurrence tree method or substitution method, you can't apply, right? And this master theorem is very important from the examination point of view. If you are going to appear for any of the entrance examination, gate examination, this particular master theorem is going to be really helpful to you people, right? So just solve few more examples related to master theorem.